Hello, everybody. Thank you for joining tinyML Summit. Today we have Stuart FEFFER from Reality AI presenting tinyML is more than models. Thank you very much for joining us again. Stuart, the stage is yours.
All right, thank you. Can you hear me okay? Am I coming through, Olga? All right, very good. So thank you. I'm Stuart FEFFER. I'm from Reality AI, and today we're going to talk about tinyML is more than models. Now, this is a hardware session, okay? And I believe that many of the other panelists here are going to be talking about hardware for accelerating edge learning, edge inference, and that type of thing. What I'm going to talk about here is a little different. We are going to talk about how to use tinyML software to make better hardware design choices, okay? Before I get into it, though, let me talk just a little bit about Reality AI, who we are and what we do. Sorry, I'm getting some some notices here through the platform. Okay. So yeah, Reality AI is machine learning software for building products, for engineers who are building products using machine learning and sensors. About half of our business is automotive, and the remainder is a mix of commercial, consumer, and industrial equipment products. Okay, we are really about non-visual sensing signals. We are not. We do not have tools for working with images or computer vision. We don't deal with speech recognition or natural language, and slower moving time series, pressure once or twice a second, temperature once or twice a second, machine log data, that type of thing. There are a lot of good tools for it. We'll come up with good answers too, but it's nothing special. What we're really about is these non-visual signal inputs, okay? And really what I want you to take away is that tinyML is really as much about the instrumentation as it is about the models. That the instrumentation you use shapes the data that you work with, and the data, of course, is the basis for everything you do in the machine learning side, okay? So many of you have probably seen this sort of methodology outline from Google. It's something they published in their pieces on MLOps and that type of thing. And, you know, it's I think this is probably the way most people think of the process of creating and deploying machine learning.
Stuart, you're on mute, so we cannot hear you if you want to unmute yourself.
How long have I been on mute?
No, it's just a couple of seconds. Maybe.
Very odd. Yeah, it went there by itself. Okay, so let me continue. You know, maybe you have seen this this methodology from Google that's in their online publications about MLOps. It starts with sourcing and preparing your data. You code the model, train it, evaluate it, and so on. Okay. Now, I think most people, when they look at this, who have actually done machine learning projects, say, gee, all I got to do is source and prepare my data. Oh, that sounds pretty easy. But in fact, that one step for most everyone we work with is 80% of the effort and expense. The actual model generation is, okay, trivial is too much of a statement, but easy in comparison. Really, this is the area where our customers spend their time and their money. So I think what you find in practice, the real process looks probably more like this. You start by sourcing and preparing your data using your best guess at appropriate instrumentation, create a model, look at how it does, and then think about what can I do to improve my instrumentation, and probably go back and collect more data. You may have multiple iterations of this. And you know, we just went through on a webinar last week a very detailed how we built it kind of process on how we did this with a model that lets cars see around corners with sound. Catch me in the Hangout after this if you'd like to hear more. But this kind of iteration back and forth between machine learning, instrumentation design, and data collection is really at the heart of what drives cost and effort in real edge AI tinyML development. Okay, so we have created software that aims to assist in this part of the process that is the most resource consuming. In Reality AI, you will find what we call AI Explore, which is an AutoML module for feature discovery and automatic model generation with explainability visualizations. This is at the heart of Reality AI, what makes possible these other modules, in particular, bill of materials optimization, where we can use the results of the feature exploration and machine learning model development to create cost-optimized component specifications, identify the most cost-effective combination of sensor components and channels, okay? And I'd like to kind of show you what that looks like, all right? Okay, so in our experience, the process kind of looks like this. We suggest that customers begin with a step where they are over-instrumenting their target. This is it. For example, we may. Sorry, I'm getting notifications again through the through the platform here. Apologize. So we over-instrument. We try to put more sensors on there that we expect to use in the product, trying to cover as many different types of sensors and as many different possible locations as may make sense. We can then, we also suggest using lab grade sensors, the highest possible quality of data and the highest possible sample rate and bit depth, because in step 2, we can use software to look at a lot of those dependencies and identify which of those combinations are the cheapest to procure, which are the cheapest to manufacture, and what the ultimate model sensitivity is to sample rate, bit depth, noise, measurement tolerance, and the other kinds of factors that may help us that determine what our instrumentation should look like. In software, we can reach an optimal set, go back, recreate our data collection rig using components we might actually include in manufacturing, and collect new data, reconstruct, retrain, revalidate our models. And now working with some instrumentation that we know is appropriate to the problem and to our economics of our use case. Okay. So for example, this is an example of a sensor selection output in Reality AI. The input for this is a set of data trying to identify, in this case, classification data labeled from a number of different channels. In this case, we have 3 different accelerometers mounted in 3 different locations on this particular piece of equipment. We have X, Y, and Z channels and so on. Reality AI then goes through and automatically constructs different flavors of tinyML model for each of these combinations of channels. And it comes back to us with the best combination of 4, 3, 2, 1 channels, which ones give the best results. We can then apply a cost function and decide which one is the best to move forward with. The other thing we can do is take what we know about the feature space and the model construction and look at sensitivity to sample rate and bit depth. We can look at our classifier and automatically downsample, automatically reconstruct the model at each point, and check and see where where a reduction in sample rate finally starts to result in a trail off in accuracy. And that can tell us what the minimum viable sample rate should be for this particular use case. Now, when you reduce sample rate and bit depth, of course, you also reduce dynamic range. So it's very important to test noise sensitivity at reduced sample rates and bit depths. And we also support that, where we will, for every sample, supplement, mix in noise data at a known signal to noise ratio and show the performance versus noise. So we can check and make sure that we're getting appropriate levels of noise rejection in our instrumentation for the given sample rate and bit depth. Knowing all of this, we can now put together a sensible set of components that will deliver the minimums required for our model, and do so with the and do so cost effectively. Okay, so let me see. Platform keeps wanting me to annotate. I don't know why. Okay, so in conclusion, like I said, I want to leave you with the assertion that instrumentation is every bit as important as algorithms. In your development process, you need to iterate on both of them and do so together. Your edge AI models can help you make better choices for instrumentation design and component selection. And of course, Reality AI Tools is a good choice to help.
Again, just a quick shout out to our sponsors. Bear with me for 1 minute. We have different categories. We have executive sponsors. First one being ARM. Then we have Qualcomm. We have Samsung. Platinum sponsors. Ada Compute. Lattice Semiconductor. Gold sponsors. BrainChip. Babel Labs. DSP Group. Edge Impulse. EMSA. Gray Matter Labs. Greenwaves. Himax. Imagimob. Latent AI. Maxim Integrated. Quixo. Reality AI. SensiML. Silicon Labs. Sentient. Google TensorFlow. XMOS. And lastly, silver sponsors, Edge Cortex, Hotchi, and Synsense.